Okay, so hopefully I'll have all my slides. So I'm going to talk about the radar modeling for ADAS and AV simulation. I'll start with a brief introduction to what we do in the context in which we develop those radars. So Claytex is, we are working in simulation and modeling of complex systems. So we're using the picture you can see here, Daimler and Modelica, in order to simulate complex systems and understand how they interact. We also provide simulation solutions and like trainings for ADAS and autonomous vehicle. But today we'll talk about our simulation solutions for the virtual driving for ADAS. So a bit of context, so the radar we develop are physics-based, and in order to work, they need to work in a complete environment. So as you can see here, there's different sensors we have to take into account: the traffic, the control, the vehicle model in Daimler, as I mentioned, and we're using RF Pro as our virtual environment instead of, I think you mentioned Unreal. So we're using RF Pro because we have, it allows us to have digital twins of cities. Oops, sorry, that went fast. Which means we can, for example, drive around in Paris, and it has also an open API, which means we can control the world in which we're doing our simulation. Here's an example of our camera. So on the top, you can see what RF Pro is showing us. And on the top right, you can see what our camera is showing. So what we want is to output the raw data of the sensor, and then we can add a layer of treatments, but we want to see what the camera is actually seeing. So you can see the distortion of the camera lens. There's also a LiDAR sensor that we're working on, and we can use the ground truth for object detection. But today we're going to focus on the radar algorithm that we're using. So it's a ray tracing algorithm. Again, the aim is to output the raw data of the radar. A ray tracing algorithm is a computational model, such as finite element method of moments, but ours is using a high frequency approximation, which means it's faster and it uses less memory than those methods. It's based on geometrical optics, which consider the wave that's being propagated as rays, and so you have a first phase where you launch the rays, and then a second phase where you trace all the rays in your virtual world in RF Pro, and you try to keep trace of everything else. And it includes also a theory of diffraction, which is not part of the geometrical optics. And we're going to talk briefly about Multipath Radar to work on what we've seen before. So the idea is you have on the one side your radar, where the user can tweak the antenna characteristics, the wave characteristics, and on the other side you have RF Pro, where you control the geometry and the physics layer, and the algorithm that goes between them is inspired from a shooting and bouncing ray algorithm. So the first step is to launch your rays. In order to do that, you can define all your parameters of your antenna. So the beam pattern, the elevation angle, etc. Here I've put a few examples that are outputted from our simulation and displayed on MATLAB. The density of the rays, if you're working on a specific radar, then you can put it into the sensor and see what you would see with it. You can obviously modify wavelength, polarization, and all these parameters. And the second part of the algorithm is to trace the rays, so to keep in track of all the parameters, all the properties of your rays, such as the power, the distance, polarization, phase, etc. Until you hit a point of impact. And on a point of impact, you simulate three phenomena: the spectral reflection, so the normal bouncing, sort of, the diffuse reflection, and the diffraction in case of sharp edges. And this is what we'll see how to do. So the reflection is modeled via a Fresnel coefficient, which sort of takes into account what the material does to the wave, to the magnitude of the wave, to be precise. So if you change your materials, you can see the quantity of energy that's reflected back. You can see on the top left and top right two examples, a first one with a rod and a second one with a metal sphere. So because the metal sphere is metal, then it reflects all the energy. But if you take something like a rod, then depending on your polarization, you'll have more or less energy that will be absorbed. A small parenthesis, the blue line that you can see is the vertical polarization that's being absorbed by something like the rod, and that's how your sunglasses work. The sunglasses would cover the horizontal polarization in that case, and so you don't see any glare. So I thought it was quite interesting when I found that out. You also take into account the roughness. So you have the surface roughness, which is going to be all the more important that it's the same size as your wavelength, but also the layer roughness. So if you have inequalities inside your layers, like, I don't know, things inside your layer, inhomogeneities, you will have diffuse effects, and those work the opposite way. So the higher the frequency, the lower this diffuse reflection will be. So by working at 77 gigahertz, we're sort of in the middle where the diffuse reflection is low enough. There's other parameters that we consider to calculate the reflection. One of them is we can't simulate all the rays from the diffuse reflection because they go all around. So we choose one or a few, but the way we calculate the power is by giving the point of impact sort of a beam pattern of its own. So depending on its direction, it will have more or less power. And you can model that using different models. This is where you have the graph with scattering patterns. I have all my graphs, I'm so happy. We take into account the polarization, as I said, but also the distance, because when you have a roughness, then the distance that your wave is going to change depending on the roughness. It's small, but it's a percentage of the wavelength, so it has to be taken into account for later on. Here's an illustration also of how we detect curved surfaces. When you have a curved surface, then your wave will spread out all the more. So we use ray tubes, and we can see if the surface is flat or if it's not. And we also simulate propagation losses. And so going back to multipath that I mentioned at the beginning, as my colleague said, multipath are due to the different paths taken by the ray in our cases, and it creates ghost targets. So on the top here you can see it's not really realistic, it's just for the sake of showing it. But you can see on the right the three spheres. So the first one is the normal sphere, and then the second one would be the sphere going like that and back like that, and the third one would be going down to the floor, back up, back down to the floor. So you can see there's a bit of a delay the radar sees the sphere a bit further away, and it's illustrated in the second picture. It's emphasized, it's not normally that strong, but it's just so you can see two spheres over there. And that's something that we need to take into account. We've been through a verification process where all the rays have been modeled and traced to make sure they were going where they were supposed to go, that the powers were correct. So you can see here you have a bunch of rays arriving, and depending on their angle, the color changes. That's due to their polarization. So we can see what we're doing is actually what we want to do, and the next step is to validate that against data. So there was a step of validation against literature where every parameter that we've added, I've shown 2 in example, a beam pattern and a Fresnel coefficient, are all validated against literature, but also inside the code, if that makes sense. So we want to make sure that it doesn't get modified because there's a lot of things happening. So we want to extract directly from the code and not just a function that does that. So we make sure that what we model is correct. And then the last step is a test, a validation. We're using a metal ball, that's why I mentioned it before, and we did some tests on specifically the ghost targets and what we could see with the radar. And the idea is to, in the future, complexify those tests and an early result. So we move the sphere around, we change the angle, we make sure that we get what we should get. And on the background, you can see here the raw output of the radar, and the blue line is from our simulation. So we could see the sphere properly. We have a sphere that's a bit thicker because we amplify the ghost target effect. And we have a power level for the sphere that is higher than in the test, and that's because of the noise that has to be added. But we need to make sure that we at least get this threshold of at least the level that we get in the test. If we should be getting more because of the noise. And so the next step would be to move on to more complex simulations and possibly to introduce other effects as well, such as, which are when your ray hits something, it creates also a current inside the layer, and this is something that we also want to simulate.